Thank you. So, can you hear me well? Yes. Everything's good. Okay. So, of course, let me join the other speakers in thanking the organizers for this lovely setup. The city is lovely, the conference is going extremely well, I'm having a lot of fun, and thank you, all of you. And also thank you for coming here instead of following the other parallel sessions, because I think they are more interesting than my talk. So let me start a little bit backwards by giving you a few references that you can consult if you want to know more about this story. I had to select a few topics about this story. I have been working on this for quite some time already. It's been almost 2 years 2 years ago when I started studying this topic. As you can see, I have a bunch of co-authors. They're all Italian, almost all Italian, but it's just a coincidence. I tend to work better with Italian category theorists, nothing personal. So in particular, Andrea Laretto is one of my PhD students. I'm going to hire Guido Boccali also as a PhD student to work on this stuff. Andrea is more on the type theory, proof assistant side of this story. I think he did a very good job, but probably his project will be different. So we wrote a bunch of papers. You see, this is the proof that I don't only work with Italians. Boiana, that is probably in the audience here, has been collaborating with us on this paper. You see the titles. This started as a very little project. It's a very nifty, a very clever proof, in my opinion, of a well-known fact that then has been turned into a completely formalized proof in alta. These studies are bicategorical structure, and it's not exactly a bicategory, but a slightly more general kind of thing. And then this is a paper I wrote alone, and it has been presented this spring in CMCS at a conference in coalgebras. So if you want to dive more into this topic, you will see that there's 3 or 4 papers that you can read. So let me start with the mathematics. When people study automata theory, they want to axiomatize, so to speak. They want to mathematize a theory of systems and processes that happen between these systems. And the category theoretic side of this is pretty old. In fact, it dates back to the 70s. And all in all, what the wisdom of this part of category theory has distilled is that if you want to study category theoretic side aspects of automata theory, you fix an ambient monoidal category, and from time to time I will assume that this monoidal category satisfies more assumptions, like for example it has countable sums, it's co-complete, it's monoidal closed, whatever I need to make this work. And the people who study automata theory with category theory want to define these categories that they call categories of milli and more automata. There is these 2 different ways of axiomatizing the kind of machine that you want to study. So you define a category where the typical object is a span of this kind. You see, you imagine that one leg of the span is a very abstract way of dynamical system, because this is nothing less than, nothing more, nothing less than a representation of the free monoid on A on X, if you transpose it. And S is a map that gives you the output, the final answer of your computation. So, definition of morphism between these spans is the most obvious that you can imagine. You map X into Y, and then you require that whatever has to commute does commute. And similarly, you define a category that you call the category of Moore automata, and A and B play the role of input and output object by doing the same trick, just studying disconnected diagrams and with a similar definition of morphism. The intuition is that in a milli automaton, the final state depends on the input. In a Moore machine, it can't. It doesn't. Of course, there is a relation between the two. You can make this precise. This was done in the paper, the semi-bicategory of Moore automata. But now I want to focus on the essential aspects of this story that, from the category theoretic standpoint, are essentially three. So, first of all, one parameter of this construction is a monoidal category. If I change the monoidal category, something like changing the scalars in a module category happens, because, for example, I can fix a monad on K, and then study Mealy and Moore automata valued not in K, but on, for example, the Kleisli category, provided that the Kleisli category stays monoidal, but we have a very well-known condition for this to happen. The monad has to be monoidal, and in fact, it's even better to assume that it's commutative. So closedness is inherited by algebras. So this accounts for the passage from deterministic machines, deterministic processes, to non-deterministic ones. Furthermore, if K is closed, there is a very neat, very elegant characterization of these categories as categories of coalgebras for functors that are quite easy to write down. You just play with the mates of the span that defines the map, and then you notice that you are just considering a coalgebra for a very specific endofunctor that depends on the parameter DB. Third, this is quite interesting because it's kind of the core of what I want to say, what I want to convey. If K is monoidal, and surprisingly, a necessary condition is that the category is Cartesian, this specific representation of automata allows you to think of Mealy AB and Moore AB as the own categories of bicategorical structures. So the subtlety is that Mealy is indeed the own category of a bicategory, a genuine bicategory. Moore AB is the own category of something that is like a bicategory but doesn't have identity one says, not always. And the absence of identity one says is exactly generated by the fact that in Moore automata, the final state can be independent from the input. This is why, and you see it playing with the diagrams. I think it's a very neat way of looking at the mathematical side of what these things are computationally opposed to these things computationally. So, this is all very nice, and people put a lot of effort in making this in honing this theory, but I think we can do better, because we are category theorists. We like things to be very sharp, not honed, but extremely sharp. And the point that I want to make in this talk is that we can use sophisticated category theory to go further and to discover that there are structures that no one considered before in these categories, but also, besides the technical aspect of my talk, I will not be very heavy on the technical details, but if you go home with a single idea, I want it to be that if you like formal category theory done in such a way that it kind of works in every two category because you're doing it abstract enough, then you're essentially doing the mathematics that explains what these categories of processes are. And I don't think this happened by chance, but of course this is a philosophical remark that needs more than half an hour of talk for a backup, but I believe in this. I think it's a very nice idea that can bring a lot of interesting category theory and also interesting applications, because people use this stuff for concrete means, for concrete problems. So, if you stare at the definition long enough that I started with, as a category theorist, you will notice that Mealy AB and Moore AB appear to be pullbacks in cut, in the two-category cut. Strict pullbacks, as strict as you can imagine them. On one side, you have the category of endofunctor algebras for the endofunctor that tensors by A, and on the other side, you have this comma category, just the same functor, comma the constant in B. These two functors are the forgetfuls, and the definition that I gave of objects and morphisms is exactly the one that realizes this corner as a pullback. Similarly, this definition of Moore AB is exactly the same, provided I change the comma with just a slice, and I take the forgetful functor. So, you can do a little bit better, because now that you recognize that this endofunctor plays the role of input, I can abstract away its role. Now, I don't look at lists of inputs, and a dynamical system that is specified by a list, but I look at the dynamical system that is prescribed by a generic endofunctor, whatever I want. And there's a whole book that studies the theory of automata in this respect. It was written by Yushi Adamek with Vera Ternakova. I invite you to look at that book. It's very elegant, it's very neat. I learned a lot about this by consulting it. And, well, you see that the comma object remain the comma object, the slice remain the slice. There is not really, like, you see where this is going. For technical reasons, then, it is more convenient to work in the case where f is a left adjoint, because these functors behave better, this pullback is better behaved. For example, it's very easy to prove that this category is complete, and this is complete as well if f is a left adjoint, but this is for the technical side. It's enough that you retain the idea that you can generalize. And now, the point is that you can generalize even more, because now the true two-dimensional category theorist in me said, well, what if we took any strict two-category, not a bicategory, with all finite limits, finite weighted limits, and then let's play the same game, let's define the same object. K, now, the category, is just a generic zero cell. The dynamics is an endofunctor, an endo-one cell, and then this theory is essentially built over the inserter, the algebras for f, some common objects, and the same diagrams. So, this generalization might appear a little bit moot, but, well, for example, you can, you can easily see that this construction depends on a diagram of this kind, and then everything I do is a limit, a weighted limit, but okay. So I'm essentially working with a sketch. These categories are models for a limit sketch, no? And in fact, this is not an entirely new idea, because the diagram I have to build is this, and if I notice that it is a little bit degenerate, because I can just collapse f with f and the identity doesn't really play the role in describing the sketch, I get this loop with an arrow, and there is someone who is considering as building block of the theory. There's a couple of papers by Daniela Petrison and Colcombe who study generalized, very abstract notions of automata, where the entire structure of the automaton is defined through this kind of diagram. Well, this approach is backed up by the fact that someone is already considering something very, very similar. I think this is a tidy way to see all the parameters of the construction in place. It clarifies that essentially what I'm doing is studying a specific limit theory. Not really surprising, very interesting, but come on, category theory has a lot of other things. Another advantage is that, well, my definition works when, for example, my constructions are based on an enriched category over a quantile. I don't know, for example, the opposite of zero infinity. And this means that I can consider not a category, but a metric space, mealy fd, associated to a non-expansive map of a metric space and a point. So what's the meaning of this? These things are computational processes, no? What does it mean that what is in this metric space? These are processes, but they have a metric, they do something. So you see that it's exciting, it's interesting to explore this generalization, not just for the sake of abstraction. It might lead to something interesting. Now, the second thing that I want to touch is, in the second half of my talk, perfect timing, is this. Well, everything I did in the very beginning, depended on a monoidal category. I can define these spans and these morphisms valued in a monoidal category. But again, what is a monoidal category if not a bicategory with a single object? So what happens if I consider the same definition, I will draw the same diagram, but not based in a monoidal category, but in a bicategory. Something nice will happen, something that has to do with formal category theory, more than with computational machines, and yet there must be a computational meaning in what's happening. So, let's play the game. Again, this idea is not entirely new, and I found a reference in Daniela's paper, on the same paper I mentioned before, because it really resembles a very old and obscure, work of Bainbridge, where he tries to model the state space of these machines as functors, and then is on the same track of characterizing behavior as a kind extension. So I think he manages to say something. It's very hard to read this paper, and I think I can say it a little bit better. So, B now is a bicategory, and instead of a span of objects, tensor of two objects into another, etc., I consider a pair of two cells. I will focus on the Moore aspect of the story. You can, of course, do both. It will just be simpler to draw a couple of diagrams, the ones that I need to convey the idea, so let's work with Moore for a second. And well, the simple fact that this span can be defined coerces the types of I, O, and E that now are one cells of a bicategory, of the ambient bicategory B, in such a way that I now must be an endomorphism, because in order to be able to compose E and I and fall into E with a parallel cell, I must be an endomorphism. So, considering the iterates of I is a very natural thing to do, because the free monoid on the object of inputs now becomes the free monad on the object, on the one cell of inputs. So, this is nice, because it puts input and output on totally different respects. In the monoidal case, where there's only one zero cell, you don't see the difference between I and O. But now I is an endomorphism, O doesn't have to be. And this fact was completely obscured by working with monoidal categories. Then, another fact. You can easily prove, if I give you the claim that the terminal object in Moore AB is the internal home of lists in A into B, you can easily prove it. It's very easy to induce the span structure that you need, prove the universal property. But now, since an object of interest is a diagram of solid arrows like this, and then an object of my bicategorical automata category is a way to feel the dotted arrows and the two cells, well, you see that you have O, you have I, it's a span, and now you're looking at possibilities to extend O along I. The terminal object in the category of bi-Moore machines that I just defined is the right extension, the can extension of the output along the free monad on the input, provided, of course, that everything exists. You have to assume that you can define you can build the free monad as an initial algebra for something, or for reasons your bicategory admits enough limits, colimits to do that. But if it does, then it's very easy to prove this, as it's easy to prove the monoidal annual. Nice. So now that you have a notion of objects, of course you want a notion of morphism, right? And you do exactly what you expect. It's a bit heavy on the diagram side, but you just do what you need to do, because now an intertwiner, and you'll see in a second why I chose this name for this notion of one cell, boils down to be a tripole of two cells. Well, first of all, a pair of one cells that connect A and A prime, B and B prime, if A and B are the domain and codomain of the one cell E, and A prime, B prime, or V prime. So you want to connect A and A prime, B and B prime, and then you want two cells, iota, epsilon, and omega, filling the diagram, such that the usual pasting diagrams these diagrams commute, these coherences conditions that arise from just writing the most natural definition. What's interesting about this? That if you do this in a bicategory, and then you go back, assuming that the bicategory has a single object, this is not the morphisms you started with. This is a new notion of morphism that no one considered before. So, you see, this is what needs to happen. And you see, this is more complicated than what the definition of morphism I started with. So, what is this? What is it exactly doing? Where I am considering this structure, if, like, considering it bicategorically and then going back to the one object case, I obtain something different. What's the meaning of this? Well, I don't have a precise answer. I just noticed in the first paper we wrote that you can do this. You can actually do it also defining a notion of two-cell. Two-cell between intertwiners boils down to be a pair of two cells that connects iota, epsilon, and omega in the way you expect. This is also not trivial in the monoidal case, which means that in the monoidal case, not only you have a notion of object morphism, which is different from the previous one, but you also have a notion of two-cell between those one cells that you discovered, the new one cells that you discovered. So what are these? What's the meaning of this? Maybe one conjecture that I have is that you understand what these are if you allow the inputs and the outputs to vary. Like if you allow every parameter of your construction to vary at the same time. Like I want to consider a category where all inputs, all outputs, all states, all A's, all B's leave at the same time, which then can be fibered over the ambient bicategory. And that's why I'm putting a lot of effort into trying to adopt this parameter-free, this approach that has a lot to do with fibrations. There is a very natural way to cook up fibration out of the definition I gave. I just gave you the definition in a single fiber, or well, in two different fibers, but without worrying how they vary. But that's probably that would take another talk. So let me instead conclude, because I think I hope I made a point that this is an interesting bits. These are interesting bits of theory. Let me show you what I want to do now, and what I am about to do with Guido as soon as he arrives in Tallinn. So, I want to apply this story, this technology, to a very specific and already interesting class of bicategories that are those that arise in monoidal topology. So, monoidal topology is a very elegant way to encode order theory and topology and metric structures all in the same conceptual framework. And it's essentially based on considering a monad on set plus additional assumptions if needed, and then a quantile. And then you define Clementino, Gavin-Seal, Vartetol, Hoffman, and others worked a lot to define these bicategories where there are like profunctors, like twisted categories of profunctors twisted by T, and the profunctors are valued in the quantile. And playing with T and with V, you capture topological spaces, metric spaces, ultrametric spaces, probabilistic metric spaces. They are a very interesting kind of category that joins together probability theory and Liouville metric spaces. So I would like to play with these definitions in these specific two categories, because I believe that now I can give a probabilistic, ultrametric interpretation for invariance that I attach to state machines. For example, behavior as a Kahn extension, as this theory of terminal objects, now acquires, just by construction, so a topological or a ultrametric or a probabilistic metric meaning. And I think this is a neat idea, and I hope I will be able to tell you a bit more about this next year, probably. So, yeah, that's the end of my talk. I hope I will be able to tell you more soon. Yes.
So, questions? Please.
So, do you cover other basic analytic systems besides localized labor function systems?
Not at the moment. I have been reading a little bit about that. I have half of an idea how to do transducers, but that's a different. You need a different technology. It's heavily bicategorical, but it's less than half big. So I hope I will be able eventually, but not at all.
My second question is special offices for interclients.
Yes.
What do they do in classical automata? How are you not found to figure out?
I try to understand it a little bit. There is a relation between this part here, iota, taken alone, is exactly what in the category of circuits, Bob Walters with Nicoletta Sabadini and Virgilio Catis, they study only this piece. They don't mention these, so I'm not really able to relate the two, but I hope this will be a slight generalization of that story, taking into account that epsilon now is non-trivial and omega is non-trivial. But I have no claim at this moment, I don't know. So if you have an intuition for these maps, and especially for the equations, I'm more than happy to listen.
Other questions? Please.
Do you have any algebraic this situation?
Algebra?
Like objects as example, instances. Like maybe algebraic eigenvalues, forces.
You mean for this definition?
Yeah.
No, I think it has to do.
Yeah, actions actually.
Exactly. I think it has to do with that, but I don't know how to make this precise. I have the same feeling, but I don't know how to make it precise. I agree.
Following up from Yuji,
Yes.
these different morphisms, classical automata theorists need to study automata. We like to study categories of automata.
Yes.
That's really good because completeness tells us things about how to construct systems out of other systems and so on.
Yes.
So really, with new morphisms, do you have some idea how the code limits change inside the category?
No, not yet. But this is an interesting. Yeah, exactly. Because for monoidal machines, completeness is everybody does it by hand. But if you read MacLean, it's one line from an exercise. Because in a pullback, some limits are created, and then you're home. So it would be nice to have that approach and to prove completeness again for this more general. Yes.
Anything else? All right, I'm looking forward to next year already. Thank you.